Okay, so let's start our today's class. And so today's we will focus on our chapter 2, so named as linear algebra and linear regression. So you can find this is the updated lecture notes in the Blackboard. So we just have some new extension part. And sometimes I would like to update. So I just have a meeting, so conflict with this office hour. So if you have any questions, so maybe you can come to my office the same time on Thursday. Okay. So today I have a meeting at this moment. Well, if you have a question, just come on Thursday. Okay. So commonly, so today's maybe we will involve a lot of kind of new content. So if you have never touched about the linear algebra and also linear regression, so just like so yesterday, so evening we have another class, so student just have a lot of questions. And if you have, so you can just first ask me so during the break. Okay. So if you still have some question, just go to the Thursday part. Well, so last week we have slightly mentioned something about the linear algebra. So like we're introducing the vector and we're also introducing the matrix. So we just stop at the page. So maybe we just have a quick review about the matrix. So matrix is just the table of the number. So it's m times n. So with so we commonly I just mentioned we will use the data to represent it. So represent it as this matrix. And this matrix have some kind of the calculation, so including the transpose, including the addition, and also including the multiplication. So the key concept that, so later on when we just handle with this matrix, the key important thing that we should always keep in mind is that when we want to make the matrix multiplication, that we should have the two matrix has a matched size. So like A is m times n, so we use this index to stand for the size of the matrix A, and use this index to stand for the size of matrix B. So we should guarantee that the m times n is equal to the n time. So this n is matching this n at this side. So n here is just stand for how many column of A, and this n just stand for how many row of the B. So if we want to use A times B, we should guarantee the number, the number of column of A is equal to the number of row of the B. Okay, just some important thing. Later on, we will just when we handle some content, so we just so this one is pretty important. Okay, and so another thing is that, so in addition to this kind of a complication, this kind of the calculation, we also have some properties for that. Well, so an important property is that, so we just we define, we have a square, we have a special matrix, so which is a block matrix, and we also define something called as a determinant, something called as an eigenvalue. And I'm not sure whether I just follow this part last week, but we just look at again. So there are several special square matrix. The square matrix just stand for the column and the row. The number of these two are the same, and there are some special kind of square matrix like the projection matrix. So which states like the a square is equal to A. So two matrices times together is still original one. And also symmetric one, so whose transpose is equal to itself. And also orthogonal matrix, which the inverse will equal to the A transpose. And a diagonal matrix just stand for all the off diagonal element is zero, just corresponding to a diagonal matrix. So we have these four type of matrix. Sometimes we will just directly call the name. So just you should just know what is the property of this matrix. Well, and we have now finished this part. And for matrix, we also define their matrix. Commonly, there are two kind of the space, so related to a matrix. So the first one is called as a range. The second one called as a non-space. So we first just look at, so just like this kind of the content, so which named as the span space. So here we just consider we have a sequence of the vector, so which is x1 to xm. And then we can try all kind of the linear combination of this kind of vector. So the linear combination just stand for we have the another kind consequence of the constant. So we consider the c1 times x1 plus cm times xm. So which means that we will use this constant to times our vectors. So each one by one and add them together. So that will become a linear combination. And so if we just consider all possible linear combination together, so that will stand for the space spanned by the vector. So with more kind of the mathematical definition, so we could write it down as this form. So it's a sequence, it's a linear combination. So where we consider different choice of the C1 to Cn. So we just try every different. So Ci is belongs to R, just stand for its real value. Okay, some real number. And this kind of if this type of set, if we combine them together, we just call as a space spanned by x1 to xn. Just stand for you try any type of the combination of this vector. So what type of other vector you can reach? So just add use this kind of a linear combination. Okay. So this is just called as a space. So spanned by a vector here. And so later on, when we just talk about the linear regression, so this is just to help us to understand what linear regression trying to do. Okay. Well, but just naive speaking, so the space span is just like originally you only have m vector, and then you now want to just use this m vector to just create it more. So you just use this type of thing to create, so try linear combination. And a range of the matrix, so is just the stand for, so the space spanned by all column vector of the A. So the range of A just stand for the space spanned by column vector of A. So for example, previously we have written down, just suppose our A is such times m times n matrix, for example. And then our A just stand for, so A11 to A1n, AM1 to AM. So here we have mentioned that there are n column in total. So n column in total here. N is the number of column. So therefore, we can just treat it as this term. We can just treat it this term, so as our x1. So we treat this term as a xn. So therefore, the range of A just standard for the space spanned by x1 to xn. Okay, spanned by x1 to xn. And so this is just so it's just like because matrix we just treat it as a collection of the vector. So the range of A just stands for the space spanned by this column vector. And the non-space just is another thing which stand for so such kind of the vector. So where A times X is 0. Okay, A times X is 0. Just sometimes we just call sometimes people will just would like to call this as a solution space of the A. So just like sometimes they solve the equation, so solve this type of equation, and the solution that make this equation equal to 0 is just this type of X. Okay, so maybe we just say two examples and we have more understanding about so the range and the non-space. So here we just consider very simple two cases. So one is called as the identity matrix. So another is the zero matrix. So just a record that identity matrix stand for is a diagonal matrix, and also or off diagonal element and all diagonal element is 1. So for example, we can write down so this special type of A maybe just here. So just stand for every diagonal element is 1 and off diagonal element is 0. Okay, so this is our A. And maybe it's just like, for example, we just say it's n times m matrix, for example. Well, and now we just want to consider, so what is the range and what is the non-space of the A. So here we have the two choice. So the first choice, maybe just for distinguish this value, okay, just use the K to stand for. Well, and the first choice is the range will be the whole space. So it's a whole R dimensional space. And the second part is just stand for the zero vector. So it's just only one thing could become the range. Okay, so it's easy to see. So just based on our definition. So here we just our K is n times n matrix. So what is our x1 and what is our xn? So follow the definition of the range. So we know we just treated this K as the n vector, n column vector. Okay, so and our x1 so is exactly so is the first element is 1. So and the other element is 0. Okay. And x2 is just the second element is the 1. So we just treated the column by column. So therefore, for example, the xt just stand for maybe stand for the tth element here. So the tth element here is equal to 1 and other thing is 0. So therefore, if we try combination, any linear combination, c1 x1 plus cn xn. So we can definitely know what is the result. So the result is like, so because this C1 times X1 just stand for this one will times C1, okay? So, and the CT times XT just stand for this element will times CT. So therefore, our result is just like this vector, right, this vector. So because our C1 and the Cn can take in any value, I just mentioned earlier. So when we just define the space, so C1 can take in any real value. So therefore, so this one can take in any vector. So this one could be any vector, just we choosing the corresponding, the C1 to Cn, we can just become any vector. So therefore, it's not hard to image that the range of this part, so it's whole space. And the non-space for this guy is just stand for, we want to create x, so which make kx equal to 0. So which making kx equal to 0. But we can just look at, so because this is the identity matrix, so any identity matrix times a vector is still the x. So this just stand for x equals to 0. Okay. So because it's the identity, you can just try that. You will not change the value of the x. So after product the k. So therefore, just stand for, so the non-space. So it's just a 0 vector. So this x must equal to 0. Okay. And you can also try the 0 matrix, stand for, we just replace that everybody here is 0. So therefore, all the x1 and xt just change this 1 to 0. So therefore, your corresponding linear combination will still become the 0 vector. So the range is still 0, and the non-space is just the so the whole space. So anybody times 0 matrix will become the 0. So therefore, any vector could become the non-space. So just to have this kind of relation. Well, so the important thing, the important thing is just so it's just another angle to look at the matrix. So it's just like, so matrix is just combined by the several column, and we treated the column as a vector, and we just want to say how many kind of the space that this matrix can reach. Okay, any question so far? Well, so this is some remaining part, so we just skip these ones. So last week. Well, next we will just back to some kind of content. So there is some content, so which called as a determinant, eigenvalue, and eigenvector. So we just briefly mentioned. So the determinant is just one type of things. So because earlier we just mentioned, so when we consider a matrix A, sometimes we are also interested about the inverse of matrix. So the inverse of matrix stand for, so that we can find another matrix B, so which make B times A is the identity matrix, and then which at this moment we just call B as the inverse of the A. So, but we mentioned that not every matrix could have the inverse. So it's just so we just involve this kind of the involve this kind of property. So whether this matrix is invertible or not. And the determinant is just such kind of the properties that can tell us whether the matrix is invertible or not. So which is written down as this kind of the result. So that matrix A is invertible. So if and only if its determinant is non-zero. Okay. And this determinant, so you may need to take some time if you forget how to calculate this. Okay. So but this is just one kind of concept. And more important is that for matrix A, so we also have eigenvalue and eigenvector. So whose definition is given as this format. So we can find a vector x, so vector x, so which is a non-zero vector, and we can also, at meanwhile we can find a lambda, so which making our ax equal to lambda times x. So if we can find this x and find this corresponding lambda, and then we will call this lambda as our eigenvalue, this x called as an eigenvector. So here this notation just stands for. So when we look at our A, so A is just such kind of table, but lambda is just a value, okay, just a constant value. So therefore, just on this type of the X, so this table or this matrix just play the same role as a constant. So therefore, you can just regarding there are just one kind of the characteristic of the matrix. So here is the reason why we just call it as an eigenvalue. Okay, it's just like the characteristic of this matrix. Well, and an important kind of the definition is that, so for n times n matrix, so if n A is n times n, so we will definitely have exactly n eigenvalue. So the corresponding eigenvalue is just the size of this matrix, this square matrix. So we will definitely have the lambda 1 to lambda n. And this eigenvalue just have important properties connecting with our determinant. So which is that, so all the eigenvalue, if we product them together, so it will become our determinant. So which is just writing down here. So all the eigenvalue is just time together will become our determinant. And we can also try that we add all eigenvalue together. So which will become things we call it as a trace of matrix. So the trace of matrix just stand for the summation of the all diagonal element of the A. So we have just just like the identity matrix. So all diagonal element is 1. So whose trace will become the size of the matrix. And the eigenvalue, if we add them together, it's also the trace of the A. So the sum of the eigenvalue is a trace, and the product of the eigenvalue is a determinant. So as we mentioned earlier, so we say the A inverse exists. So it just stand for A is invertible. So it's if and only if that are determinate. So it's non-zero. And we also know that the determinant of A, so is the product of the eigenvalue. So if we want the product of the eigenvalue is non-zero, just stand for none of the eigenvalue is 0. Okay, just everybody is non-zero. So this is just matching our earlier statement. So eigenvalue is just the one characteristic of the matrix A. So if you want A could take in the inverse, we just need to guarantee that there is no characteristic like the 0. So because 0 do not have an inverse, so just like everybody is non-zero, and then we can have the inverse. Okay, so this is just some key kind of the important things, so related to the matrix. So just like the eigenvalue here. Well, maybe we can just just go to another page. Okay. So and this sometimes we want to so build more connection between our matrix and the eigenvalue, because eigenvalue just we just say it's ax times a times x equal to lambda x, but it's not clear. So how could use the lambda to represent it our matrix A here? So but there is some special case. So if our A is a symmetric matrix, so which stand for that the transpose of A is equal to A. And at this moment, so we can just consider the spectral decomposition. So the spectral decomposition is just stand for, we can just find a matrix U here, which is a orthogonal matrix. And a orthogonal matrix just stand for that U transpose is equal to the inverse of the U. And then we can also create another diagonal element, so which is our lambda. So it's a capital lambda here. So which is a diagonal element. So whose diagonal element is just the eigenvalue we have seen before. So lambda 1 to lambda m. So and our matrix A could eventually be written down as this orthogonal matrix U times this orthogonal matrix, this diagonal, this orthogonal matrix U times our diagonal matrix and times the transpose of this orthogonal matrix. So it's also just stand for the U inverse, okay, because they are just the same. So this is some key properties. So we will use later. So when we're talking about for the kernel or ridge regression, or sometimes you can also just like if you have ever know like the principal component analysis is also just use this. Just first told you like this spectral decomposition, and you just keep some largest eigenvalue part and just delete others. So just the main idea is just based on this spectral decomposition. So you can build the connection between your eigenvalue and also our matrix A here. Okay, some notation. So we will. So if you feel it's confused, but just the first we put out here, so you need to have a memory about that. Okay, so once we call them, you can just back to this page to look at the definition. Well, maybe we can just see a simple example. So that here we have the matrix D, and we want to do the spectral decomposition. So this spectral decomposition always hold for the symmetric. Okay, we should guarantee our matrix is symmetric. Okay, which stands for the D transpose equal to D. So of course this guy is true. And given this type of the thing, we can just find the corresponding matrix U, and also our diagonal matrix, so which is built by our eigenvalue. So or we can find two eigenvalue here. One is 3, another is a 1. And then we just write down this diagonal element. And this U could be also created. So and this U is just such kind of the orthogonal matrix because you can just trying to write down the transpose of this term. So you can check. So once you use this U times the U transpose, you will get the identity matrix. So just like this one times this one, so you will get the 1, and this row times this column, so you get 0, and so on and so forth. So you can eventually get this U. And you can also check that with this U and with this gamma, this not gamma, it's a capital lambda. And we can just find D could be represented as this 4. So this just give us a key kind of the features about symmetric when our matrix is symmetric. Okay, and so this is also the most common matrix we will meet. Common matrix we will meet. So because sometimes in a lot of time we just handle with this type of matrix. So this orthogonal decomposition or spectral decomposition is pretty important. So, but don't worry. So if you just keep in mind first about this kind of content. And the last thing we will also use later today, so it's called as a quadratic form. So it's just a case that we consider. So given a matrix A, and it's also symmetric metric, and we wondering, so what is the value of the X transpose A times X, X transpose A times X? So here our X is a vector. X is a So it's a m dimension vector. So therefore, just like our A is m times m, so X is m times 1, and X transpose is 1 times m. So this whole thing will eventually result into a constant, And so whose value is just can be computed at this form. So it's just looks like we try different value of I and j, and then we consider use the ij's element in A times xi and times xj. So just try different ij and use the corresponding element in A times xi times xj, and that will result into our quadratic form. And sometimes this quadratic form also play a role just to show, so what is the relation between the eigenvalue. So here is just a properties for this quadratic form. So once we can try every kind of vector x, so if we can guarantee that x transpose ax is always non-negative, so we will call our matrix A is positive semi-definite. So, and if we can just remove this equal to 0 to larger than 0, we just call this one as a positive definite. Okay, so just the x transpose ax is always positive. So for all vector, so except the 0 vector, and then we will call A as a positive definite. The things that is built a connection with eigenvalue is that, so the positive definite is also have a equivalent statement, so which stand for or the eigenvalue, so is larger or equal to 0. So this stand for the positive definite, and the positive semi-definite. And the positive definite also is equivalent to all the eigenvalue is larger than 0. Okay, so some kind of things we will also use later today. Well, just some kind of the how to say, some kind of the knowledge is in the linear algebra. Well, so if you just feel confused about some part I just mentioned, so just ask me during the break, okay? Just ask me during the break. Well, so this is just some remaining content. So in last week. And next we will just build on this type of the linear algebra to reconsider our regression problem. So before that, we just have a review about the regression problem. So this is truly our today's content. So it's our first. So if you still remember, so we just mentioned we have the 4 type of the task. So the regression, so classification, also we have association and the clustering. So regression is our first part. We will use 3 weeks to handle. So for a regression problem, we just have our data is given as the zi and yi. So just suppose we have the n data, and we use the index, so I from 1 to n to stand for the index of data. So here, the zi and yi just have the 2 kind of the role here. So zi we call it as an independent variable, and also is commonly thing we call it as a feature. So, and yi is our target variable. So it's also called as a dependent variable. So in regression problem, so if you still remember the things in the chapter 1, we mentioned that in the regression, we just want to build the connection between the zi and yi. So which means that we just want to find a function f. So which making the fzi is close to yi for any I from 1 to n. Just I from 1 to n. Okay, so this is our task here. Well, but just before that, so maybe you can just think for a while. So about how we just finish this type of task. So what is a way to find such kind of function f to making fzi close to yi? So maybe we just consider that our zi is just a very simple. It's just a 1 dimension. It's just a constant, okay? And yi is also a constant. So maybe just to consider a simple case that z, I, and yi just a 1 dimension. And of course, a natural way is that we can, if it's possible, that we try any f, and then we just pick 1, which is the best. So the best just stand for the fzi will close to yi. So here, but we can just think about how many f we could have. So f is a function. So it could be any function between, maybe I write down. So it could be any function from R to R, from R to R, okay? So R is the real value, and it's just a stand for the real space. So it's just a mapping the Z to Fz. And we just want to make fz is close to the y. But we just find so if we can just search all the possible functions, so here all the possible function which is R to R, and then we can just it is possible that if we can search and then we just need to pick the best one, and then that will become RF. We just pick the best one whose F will making HZI close to YI, then that will become RF. But there will be some kind of issue. It's just because so this space is extremely large. So in mathematical way, we can see the dimension of this space. So is infinite. So which means that this space, the number of this f so is extremely large. So we cannot do that. So we cannot do that. So therefore sometimes we need to use some another understanding to solve this problem. And the way that you probably have done before, this way is just we call it as a modeling. So mathematical modeling. So the modeling just stands for now. So our original task is just trying to find a f here, but while f is so large, so I just want to make some assumption on the f. So just stand for f have some structure, have some property. So that is the way we call it as a modeling. So and today's we will just focus on a special type of modeling. So we just assume f is a linear function. So which means that we just assume that linear function just stand for, so fz may be equal to some. So beta 0 plus beta 1z. So, and now this is a linear, it stands for a linear function. So linear function now, our original task is trying to all the f. So here we just try to all the linear function. And so our just the task is changed. So originally we focus on how to find a f. And now we just change to how to find the beta 0 and beta 1. So because once we fix these two values, we just have a function. Well, so this is just the common thinking that how we handle the regression problem. So of course, the major issue is that we cannot handle all the f. So you just build on some assumption on the f. So by this assumption, later on we will say it may not just you just say everybody could be a linear function. Of course, you should look at the data. So based on the data, you can make such kind of assumption. And another way, you can also try some other things like you can try this one, the quadratic function. So it's quadratic function. So of course, it's also fine. Okay, quadratic function. And you can try any different approach. So for example, you can try this guy, it may be like the forward neural network. So it's just given like the Z is a network. So network, you know, is also just a function, depends by some weight and depends by some bias. So, and for this different kind of task, so all these functions just have the explicit form. So you have more kind of understanding about your f. So it has the explicit form, just stand for you know what is the mathematical definition here. But here, this f, we have no idea about what is the structure of this f. So you can assume it's a linear structure, it's a quadratic structure, or just like the neural network structure. And we just change our original task trying to search all the f. Now just search the beta. So search the also 3 beta, and here you just search about the bias and the weight. So, and also you can try some other. So just like any other function like the transformer, and they always have such kind of the parameters, just like the beta or just this W and B here, which is commonly called as a parameter. So what we are trying to do is just trying to search the best parameter. So you know what we focus on. So originally it's a whole space F. Now we just focus on special type of F. So like F is a linear function, like F is a neural network. So they are just the family of the class, just a part of the function, not every, just not like all the possible function here. So this way we call it as a modeling, just because we make assumption on them. So because we cannot handle that so complicated question, so we just make our question simple, and then we can just or just change to solve originally need to find or infinite dimension, but here you just need to search on 2-dimension unknown constant. So 3-dimension, and also this is the dimension how many unknown parameters in the network. Well, so this is the overall idea. So we're just making that kind of assumption on that. Okay. Let's just look at one concrete example. Okay, a more concrete example. So now I just plot a data. So the z and y. So here we use this kind of line to stand for the value of the z, and the vertical line stand for the value of the y. So each blue point just corresponding to a data. So if we focus on just for easy of understanding, if we focus on this special data, so whose value, whose corresponding zi is just the height of here. Okay, this is our yi here, and the corresponding xi is the length of this part. Okay, this is it's not xi, it's our zi here. So, and if we're given the zi, given yi, we can just plot every data in this two-dimension plane. And then all the blue point is the things we just, is just all the data here. You can first ignore what is the read line here. Okay, just ignore this read line. So now just given this type of function, just given type of this of data, so you can also we can also just starting from our original task, like we want to find f to making fzi close to yi. Okay, so of course you can definitely find a very good function, that making your fzi is exactly equal to the yi. You just this function is just like you connect all the blue point. Okay, just connect all the blue point, and then this function just stand for the fzi will exactly equal to the yi. So if you just use a line to connect all the blue point, and then the corresponding function just stand for fzi will close to y. But of course, that approach just looks like a little weird. So the reason is like that. So this type of function may just have a good kind of performance on our given data. So if some other new data come in, we want to test this function, so it may not have a good performance on that. So therefore, commonly, so we do not just we just do not just have such kind of the thinking that making the fzi just exactly equal to yi. Okay, just like for this type of cases. Well, so because this may not can tell us anything, maybe it's just the function, but it does not have any kind of meaningful. So the more important thing, sometimes we just want to detect, so what is the pattern of the zi and the yi. So here, just like we can just, if we just look at our data, so we can just find such kind of the tendency, so between x and y, or between z and y, just this type of tendency. It's almost like a straight line here. It's almost like a straight line here. So, and just built on this idea. So we look at our data. So we have more understanding our data. So maybe we just come up with a kind of thinking. So whether this yi and zi will have such kind of the linear relation. So linear relation just, the linear function. So in a two-dimensional plot is just a straight line. So stand for the linear function. And so our question, or just our thinking, is just whether they have such kind of a linear relation between this type of the have this linear pattern. So within this type of data. Okay, so but of course, if you find sometimes this one may be plot like a quadratic function or like some smooth function, so have some kind of periodical or some other kind of pattern. So we should based on our data to build our model. Okay, so just first have understanding about them, and then you can have some assumption on that. Okay, so the key idea is that we don't want such kind of ugly function to connect all the point. So maybe it cannot be representative for our data. It's just some mathematical matching. Okay, now just based on this data, so sometimes we have this type of the linear regression. So we just suppose it's a straight line. So our data is played like a straight line. So we have assumed that maybe the underlying pattern between zi and yi is just have a linear function. So this just come up with our thinking. So maybe fzi is equal to some linear function. Well, but the remaining issue we still have, just like we cannot, so this is in geometry that we know. We have such kind of a blue point. So we cannot guarantee that a straight line can connect all the points. We should further to trying to have some explanation on why. So given a straight line, so why there are some kind of discrepancy between the line and also the corresponding observation. Okay, so maybe we have a quick summary. So it's just like based on data, we have this type of the guess, this type of modeling that our f may be supposed like a linear function, but it's clear that this linear function, so for any given zi, it will not equal to yi, just because there are such kind of discrepancy between our line and our data. So therefore, we should add some explanation on that. So this explanation is that we're adding something called as a noise here. So we just according there are some randomness. So when we're collecting data, so it's just stand for the underlying pattern. So maybe the linear, but there are, so it's in real world when we do the data collection. So there are some kind of noise will come. So which making there are slightly discrepancy between our x and between our y. So between this linear function and this corresponding observation. So therefore, we're just adding a noise term, so called as epsilon I. So later on, we will just have a more kind of thing to talking about this epsilon I. So once we later on study the property of the beta. But here, the things epsilon I just stand for some random variable, and random variable just stand for it's a random, so it could change. So for different I, so this epsilon I could also change, and so we just call it as some randomness here. Okay, so this also just have an explanation why different time the discrepancy is also the different. Sometimes the data is above the line. Sometimes the data is just in the below of this line. Okay, and now we just have our model, so which is yi equal to beta 0 plus beta 1 zi. So add the epsilon. So here is just the one dimension case. Well, so it's just this once we just build this type of model, actually we just make assumption on how the data is generated. So the data is generated according to this model. So in just we have assumed on the generative mechanism of our data. So which just states that any R observation so is generated by this linear function. So, but of course, this corresponding beta 0 and beta 1 is some unknown things, And this is something that we're trying to figure out. Okay, we just know it's linear relation, but we don't know what is how the value of this linear relation, what is the value of beta 0 and beta 1. And so our next step is just trying to so this is our generative mechanism. Okay, generative mechanism. And we just want to find what is the best beta 0 and best beta 1. So according to our data. Well, so this is just so in most of undergraduate level course, so we will just focus on the one dimension case. But we are just a postgraduate, okay? So we will just directly go to the multi-dimension case. So here, we at this moment, we no longer have only one feature. We will have the R feature. So the R feature stands for that a single data is played as a role as a Z1 to ZR to stand for the first feature to the R's feature. So here Z1 and ZR we just called earlier. So it's a dependent variable, and it also have some other name like the feature, like the predict variable. But they are just also stand for the same things that we want to use this data to represent our Y. So our Y is our response variable. It's also still one dimension, and also we also call it as a target. So a single data is just looks like a Y. Maybe we just use our yi, zi1, zi2 until the zir. So this is what our data looks like. And we just have this model. We just assume that they have a linear relation. Okay, y is equal to this linear combination of the zi1 to zir and adds our noise term. So it's pretty straightforward compared with our previous part. Pretty straightforward, okay? So this is just our assumption or our assume that this guy will lead into this corresponding observation data. And of course, our next step is just trying to figure out what is the corresponding beta 0 and the beta r. So something we're trying to do next. And so this beta 0 and beta r is just some underlying. So first of all, there are some underlying generating mechanism, and we want to use our data to recalculate what is the value of them. And epsilon is just the noise we have mentioned earlier. So if I just stop at this point, so we just stop at this point. So if we so commonly we just call this type of one as a linear regression model. But unfortunately, so it's just missing some assumption here. So missing some assumption here. So if somebody asks you what is a linear regression model, so you cannot say this is your answer. So linear regression model have a 3 key assumption here. So maybe you can think for a while about what kind of assumption I just missing here. So this things is just depends on, so it's just related to some kind of probability content. Okay. So okay, so maybe I just see the answer. Okay. So the first thing is that we should have assumption on the epsilon. So the first cases is to say that this epsilon. So here we have the n data. So we have the n data. So therefore, our yi is looks like the beta. Let me just rewrite. Okay, so we have the epsilon here. And we call epsilon is some random variable. It contains some randomness. So the random just depends on at the different realization, this beta I may just have the different value. But the key assumption is that the first thing is that epsilon 1 to epsilon r, epsilon n. So they are independent. So this type of thing we will mention later. Independent. And identically distributed. Just stand for, even though they are random, but the pattern of this random are the same. So stand for the commonly we will say it's just like the distribution of this random variable will be the same. And the second thing is more important, is just to state that the expectation of our epsilon I so is 0. And the variance of epsilon I is sigma squared. So expectation just stand for, so epsilon I will take in the different value. So it's a random variable. So at a different realization, it will take in the different value. And the expectation just stand for the average value it could take. So it just stand for the average value must equal to 0. So okay, must be equal to 0. So it's very easy to understand. So if this epsilon is just, the expectation is non-zero, just like the 1. So it will definitely have the influence on our estimating over the beta 0, okay, over the estimating over the beta 0. And commonly, so in some earlier kind of the statement, the people will just rewrite this part as a epsilon I becomes a normal random variable, okay, normal random variable. But actually, this kind of assumption is not such kind of necessary. So expectation and variance is enough. So, but there are some special, so sometimes you would say this one to replace this notation, this kind of assumption. And the third assumption is like that. So our feature are independent. So with epsilon I. So our feature should not have relation with epsilon I. So it's also easy to understand. So if our epsilon I presented here is like the zi1 square. So of course we cannot have any, of course, maybe as a cubic, okay, as a cubic. So power of three. Of course we cannot say that this guy, this term is this whole term is a linear function because you definitely have a polynomial term here. Okay, so the third thing is that we should have the non-relation among the R feature and R corresponding noise here. So this one is a key kind of things to distinguish the linear model with some other econometrics model. So in some economy theory that they don't have this type of assumption. So that will be called as another name of model. So but for the linear regression model, we just have these three key assumption. Okay, so once we have this assumption, we could say that this model is a regression model, linear regression model. Okay, so maybe we take the 10 minutes break and we can discuss if you have a question about this part. now we already have the linear model. So next time we will try to use this model to represent all the data. So here we have the observation yi and also the zij. So zij stands for the jth feature in the ith data. We just write it down here, jth feature in the ith data. And now we have the, we just assume the unknown. So we just assume the unknown, the parameter. So we just have this linear model as our generative mechanism. And the unknown thing is this beta, okay? Unknown thing is the beta. Now we can just write down the whole things. So our first data is presented as things I have shown before. Second data is here. So just the same as the things I presented here. Now, just for nth data, we can have the n equation. But sometimes it's not such kind of convenient to write down every equation. So we can just rewrite this part as our matrix form. So the key observation is that we can find, so in this block part, this block part, so we can find everybody is just a type with the beta 0 to beta r. So which just play just like the matrix multiplication. So this looks like everybody is times with a vector. So beta 0 to beta r. So therefore, our consideration is that we can rewrite this middle part from beta 0 to beta r. And then, so what is the remaining part? So which type of matrix will times this beta? So we can just look at, so which type of matrix will type this beta. So in this, so first of all, if we have such kind of matrix, so the first result is this one. So it looks like it's a 1 times beta 0 plus z11 times beta 1 and z1r times beta r. So which means that this value we can write down. So it's our 1, z11 until the z1r. Okay, so this is our first, so actually exactly the feature. So in the first data, exactly the feature in the first data. And second one is z21 to z2r. So on and so forth. So last one will become 1, zn1 to znr. So we can easily to check. So like use this guy times this column vector, so which will result into this summation. And also, like in for second part, we use the second row to times our column, so which will result into beta 0 plus beta 1 times z21 plus until beta r times z2r. So same as this term. So this block part, we can rewrite it as a matrix times a vector. And this part, we can write as another vector. And our y is another vector. So we can rewrite our whole equation as a vector equal to a matrix time vector as another vector. So we can just simplify the first term as a matrix y, vector y. So it's a n-dimensional vector. And the intermediate part, so this guy is a matrix z. So it's n times r plus 1. And our beta is r plus 1 times 1. And our epsilon is n times 1. So which resulting our data could be represented as a y equal to z times beta plus epsilon. Okay, so this is how we use a matrix to represent our data. And the remaining issue is that it's still back. So it's just a form of to rewriting the data, but it's just a more convenient that you don't need to write this type of the several equation, and it's more organized here. And now our remaining question is that, so how we just find the beta 0 and the beta r? Okay, so let me just use this page. So the remaining question is that, so now we have our data. So our data is presented here, and we want to, next step is trying to find the best beta 0 and beta r, which can making the corresponding z beta, the linear part, equal to y. And of course, so commonly, so when we look at this type of form, so we sometimes call this one as a linear, linear function, so linear function. But unfortunately, so this epsilon is unknown. So we have no idea about the epsilon. It's a random variable. So which means that we may not can get this corresponding beta 0 to beta 1. So the best one, so the underlying one, okay? So therefore we can just need to estimate. So what is the beta? So just at the same point, we want to find the beta to making the z beta is close to y. Well, so now what kind of the solution to that? So of course there is a naive approach because we want to find the best beta. So the best beta should making z beta and y as close as possible. The z times beta just stand for your first prediction on the first data. So it's just a given. So given any arbitrary beta, so you can create your prediction on the y1 and also your prediction on the y2, so on and so forth. So given any beta, you will have the n prediction. So we need to guarantee our n target is close to the n prediction. So this which will result into our square arrow. Okay, our square arrow. So we can just define an arrow function. So we can define a function like z times beta minus y. So it's a vector. So we want to making z beta is close to y. So which we can use a norm of this vector. So it's just a stand for the length of this vector. We want this length as small as possible. So if this length is 0, just stand for z beta is equal to y. And but we may not be able to achieve the 0. So we just want to make this one as small as possible. So which will result into our function here. So our function s, so it's given as a, so we just want to make the, so this is our y, and this is a j's kind of target. So and given n in b, so this is our corresponding prediction on the j's data. So it's a linear combination. So with the zj1 to zjr, and b is some any given value here. And it could be formatted as a y minus zb transpose times y minus zb. So it's the same as the things we have written down before. So the norm. So sometimes I will prefer use the 2 here because later on we will have the 1 norm. So but it just stands for the Euclidean distance. Okay, Euclidean distance. The same as the norm we have shown the earlier page. And now our question is like, so this is our target function. And we want to find a b such that this one as small as possible. So maybe we can just go to a new page. We have a function s, so which is written down as a y minus zb square. And our best beta, our target beta, we just write down as a beta hat. Okay, so it's a eigen mean of any kind of choice. It's a r plus 1 dimension to making y minus zb as small as possible. So this eigen mean just stands for, so the value of the b to making this guy achieve the minimum. So which stands for the eigen mean. So eigen mean. So where is the mean? Stand for where is the mean of this function? Well, this is a function over the b. So y is our observation, z is our observation. We can look at from the data, but the unknown thing is the b here. So it's a parameters we want to estimate. So now our question is that, so we are to find a b here. Well, so it's just a very, very old story question. So maybe have a review. So here, just to have a review about a one dimension case. So we have already we always find we always have such kind of a question like find a minimum of a function fx. So we have a fx, so it's a one dimension, and we want to find minimum of fx. So this is a very, very typical question in the calculus. Okay, typical question in the calculus. So given the f, how we find the minimum of fx? So, and here is also the same. So given a function s, how we find the minimum of s? So we need to know where is the smallest one, and also where we should know where we can get this smallest one. So if you still remember, so we can have a, so if you still remember, you know, there is such kind of theory, old theory say that the minimum will must achieve the point where the derivative of this term is equal to 0. Okay, derivative. So which we use the derivative function f prime x. So commonly it's written down as a differentiable over the fx, the derivative over the fx. So, and we just know, so actually it's not just, we just the minimum, if it has a minimum value. So its minimum value must satisfy that f prime x equal to 0. Okay, so this is a place where we find the minimum. So commonly, so we just consider the derivative equal to 0, but maybe it's maybe corresponding to maximum value or corresponding to minimum value. But once it's just, so it's if it has the minimum, it must at this point must satisfy this value, f prime x equal to 0. So the f prime x equal to 0 just stand for where is the place that we can get the extreme value. So if our fx is just a one dimensional from R to R, so with no any constraint. So this guy, we just focus on solving this kind of the issue. So solving this kind of equation. So f prime x equal to 0. And now we just, and here we just go to the multi-dimension case. So it's R plus 1. So for example, consider a k dimension case. So where Rf is Rk to R. Rk to R. So it's mapping a k-dimensional variable x, which is from x1 to xk to the fx. Okay, so commonly we can write down as a fx1 to xk. And now we also want to target the same question, how we find the minimum of fx. So we just want to find the minimum of this fx. So it's written down as this form. So we just slightly change the derivative, so which just have that name as a gradient. So commonly we will write down as a nabla fx, so nabla fx. So it's just defined as a, so first of all, it's a k-dimensional vector, just depends on how many x we have. And it's defined as a, so the first element is a partial derivative, so over fx. So partial derivative for the first x. And the second element is a partial derivative over the second element, x2. And the last one is for the last element, fx here. And now we have our gradient, nabla fx. So it's written down as this form. Well, the things will play a same role that we want the nabla fx equal to 0. Okay, so this is the idea that, so we just believe that minimum must achieve, so over the place that can make it nabla fx equal to 0. So this is also the way that why later on when we just talking about the neural network optimization, problem. That's why we always just use a gradient. Okay, use the gradient. It's just because we want to find the place where this gradient is 0. Okay, so this is the answer, how we find the minimum for any arbitrary function. So of course, here I just want to emphasize, it does not satisfy every solution from here can be a minimum of the fx. So, but the minimum of fx must satisfy for the first derivative here equal to 0. So sometimes we just call this as a first moment optimality. First moment optimality. Okay, now our next step. Okay, let me ask any question. Wow, just some calculus content, just corresponding to the derivative equal to 0. So it's how also the important role of this derivative. Okay, our next step is that we will try to find the minimum of this S function. So we just follow the same slides. And now our F, so it's given as a Z, let me rewrite. So Y minus ZB. Okay, so this is our F. So I just keep this notation. And now we just wondering, so what is the lambda FB? So just stand for here, our B is the R plus 1 dimension. So therefore, the lambda FB is also must be R plus 1 dimension. And we just need to take the partial derivative for B1, B2, or B0 until the BR. Okay. So what we are trying to do next, we're trying to calculate. So what is the value of this guy? Well, it's just like a little complicated though at the first glance, just because we just have a matrix involved. It's not like this fx. Just to have a quick review about some very earlier question, just like this k dimension. So sometimes in our calculus course, we just heard about like, for example, for a 3-dimension case. So we consider the fx1, x2, x3. So maybe written down as x1 times x2 plus x3. So at this moment, we can easily to figure out, so where is our nabla fx? So we just take the partial derivative for x1. So we obtain the first element is x2. And we take the partial derivative for x2, we just get the x1. And we take the partial derivative for x3. So we get the 1. So the partial derivative just stands for, we treat it, if we take the partial derivative for x1, we just treated all the any other argument as a zero, as a constant. So therefore, this constant times x1 plus some constant, so whose partial derivative will relate it to this x2. And it's also same for the x1 and the 1 you can obtain. But at this moment, it's just more complicated. It's not like just like have this kind of clear format. So this is something that we need to do to handle. But the idea is also the same, that when we're taking the partial derivative for like the beta 0 or b0, so we're also treating the others as a constant. So we just look at the things one by one for this kind of element one by one, and we can find the result. Okay, so this is something that we will take some time to do. Well, so of course, the most straightforward approach is that you write down the whole part, and then you just take the part derivative one by one. Of course, you can obtain the solution, but here we want to do some more smart way to do that. Well, so this is just the cases. Now, let me just use another page. Now, let's just back to our function here. So we're wondering what is the gradient for this guy. But first, we can just make some simplified version. So when we just first come to this length or just the norm square, we just know this guy. we can write down this guy, the earlier stage. So it's y minus zb transpose times y minus zb. So we can first make some decomposition over that. So the first term will become y transpose minus zb transpose, and times y minus zb. So we're taking the transpose inside. And then it's just like this element minus this element times these two elements. So we just conduct this multiplication. So first we will use y transpose times y and zb. So we obtain y transpose y minus y transpose zb. And second one is zb transpose times y. And the last one is zb transpose times zb. So some key important thing is that, so our y here is a n plus 1 dimension. And zb is also n plus n times 1 dimension. Okay, so because the same, we can just make this kind of the minus here. Okay, so therefore this guy is the constant. So this guy is also a constant, and a constant for each. So if we want to take the partial derivative for the b, so we just look at where is the b we have. So here have a b, so here have a b, and here we have a b. So this type we can just ignore later. But we can just change this one. We can organize this result a little bit. So the first one could write down as the y and the y, the inner product. And the second one is the y and the zb, and the minus zb and the y, and the plus zb and zb. So here, we actually notice that they are just the same because the change inner product, so the x and y is equal to y and x. So therefore, just to change a little bit. Okay, it's just become, this is our final outcome. So it's very like when we just handle like the a plus b square. Okay, so it's will given as a it's just very like the way we calculate the a minus b square. So it's a square minus 2ab minus b square plus b square. So it's so this is our a, this is our b. So a square minus 2ab plus b square. Okay. And our next step is trying to do the derivative or nabla for gradient for this term one by one. Okay. So the first one will get 0. So it's easy to say there is no b here. And the second one, we will try to do this one and trying to do this one. Okay. So here we can just make such kind of the observation. So the first observation is that, so nabla for any ax times c part, so this guy will equal to a transpose times c. And second argument is like for any ax times bx, so this guy will equal to a transpose b plus b transpose a x. Okay, so we have this kind of the result. So therefore, if this two is true, so it can just following this format and this format. Here you just treated b as your x, and a is equal to the z, y equal to the c. So you know this result will become z transpose y. And the zb and the zb is just like you treat the z as a, this z as a b. So you obtain that is z transpose z plus z transpose z and times b. So if everything could, if these two things are true, so we can find the result. So it's just follow the same things that when we take the derivative. So it's just follows this guy is 0, so it's adding this the derivative minus the derivative of this part and adds the derivative of this part. It have this linearity among this derivative calculation. So next we will just trying to show the 1 and the 2. Okay, maybe write down as a proof. Now we want to find the ax times c. So it's more better to write down what is the form of this ax and c. So ax and c are any arbitrary matrix and vector. So here are a, maybe I just use the m times n vector. X stand for n times 1. Oh, this is a matrix. This is a vector. And the c is a m times 1 vector. So first point out the size. And we want to calculate, so what is the derivative for ax inner product with the c? So first of all, so we can based on the definition. So this term will become the ax transpose times c. So it's a x transpose times a transpose of c. Well, it just looks like, so it just looks like this kind of format. So, okay, and we can just do this once again to, and we can just treat this thing as a two-part. So one is the x, another is the a transpose of c. So a transpose of c, a is the m times n matrix. C is m times 1 vector. So a transpose of c is a n times 1 vector. So this is something we mentioned earlier. So why the multiplication is important? We just need to remember what is the size of this term. So it's n times 1. X is also n times 1. So we can rewrite this guy, a transpose of C, the first element. So it's have the n element in total. So just the stand for, use this one to stand for the element. And now we can compute what is the value of this term. Just suppose our x is also equal to x1 to xn. So therefore, when we just calculating the inner product, the whole thing is that use this term times x1 plus the second term times x2 and plus this term times xn. So we can find it's a transpose c first term times x1. So this is our inner product. And we want to take the derivative for this, the nabla for this guy. So we are actually trying to do the partial derivative for each. Let's just look at them one by one. So what is the partial derivative for this term? So we have already know Ax transpose C. Ax inner product with C is given as this term. So when we take the partial derivative for x1, so it's just only have this term with the x1. So therefore, the result must be this one. So this one is a constant, okay? It's a constant. So we just say it stands for the first element in the A transpose of C. And also, when we're taking the partial derivative for x2, the only thing is this A transpose C, x2, the 2 part. And so on and so forth. So the last one is A transpose C, the nth element. Okay, you probably know what is our solution. So this term have no difference compared with this term. So it's a transpose of the C. Okay, it's a transpose of the C. Maybe we just remove this part a little bit to here. Okay, so we just finished the first part. So the AX, the partial derivative for AX C is A transpose of C. It's not, it's the gradient, okay? So actually, so it's just told us one result. So what is the result if our variable, so it's one part in the inner product, it will become the transpose of this A times the corresponding C. Okay, so this is just here we actually use some kind a little type of trick, but you can of course trying to write down all the matrix A and all the vector C and trying to do it step by step, and you will definitely get the same answer. Here we just use some trick. Okay, I first reorganize this part. I don't want to know what is the inside of A, so I just combine these two together. Well, but how we just remember these kind of things? Actually, it's a little bit easy to understand. Just like if our A and X and C are, they are all just some constant. They are all some constant. You probably know how to take the partial derivative. So if everybody is a constant, so inner product just stand for the time. So X times C. So if we take the derivative, so we will obtain the A times C. So AC will be our result. So, but we're just curious about, so how, but when we just both becomes a multi-dimension, like A is M times N, C is M times 1. So this result will become A times C. So of course, it's not true. It's just because A and C, they are not matching the size. So, and we also know the partial derivative must become, the nabla or the gradient must become N times 1 vector, okay? So in this case, it must become, I just use a, wait a moment. It must become N times 1 here. So you need, so, but the key things is that you just reorganize the A and C. So A is M times N, C is M times 1. How you just making the A and C can creating N times 1. So it's just use so this one is not true. So just use A transpose C. Okay, so this is a way how we just how we remember this one. So actually, what I want to emphasize that so actually the matrix product is does not have any is not just a kind of the difficult thing. It have a very close relation for the one dimension case, but for the one dimensional version, the transpose is equal to itself. So therefore, when we just handle the matrix form, we should be very careful. Okay, just because that so a just because the transpose version. But if we know the result, the dimension of the result, and we also know the matching size, so like A and C, if they want to match it together and creating an N times 1, we can only have this choice. So A transpose of C. Well, just some trick to remember. Okay. Well, this is for the first part. So if we are not quite sure, you can try do this one again. So as an exercise, so just a little bit complicated, but it's just a good way to help you to get more familiar with this type of the linear algebra. Okay, our next name, we will focus on the AX and BX. So this guy will be a little more complicated. But of course, when we handle the AX and BX, we can also do the same things to first write down what this guy is. So it's a AX transpose times BX. So which will result into the X transpose A transpose times BX. Well, so it can write it down as a X transpose. So with A times A transpose times BX here. Well, so we can just treat it AB. Maybe I just write down additional here. So it just can treat A transpose B as a whole part, whole part. So here we also assume that our x is we just assume that our x is n times 1 vector, a and b. They are m times n matrix. So therefore, A transpose of B is n times n. So this guy is n times n, n times 1 times n. So for each X transpose, A transpose B and X for these three kind of the size. And well, so this one, if you still remember what I mentioned, so this is a quadratic form for the A transpose and the B. Quadratic form for A transpose and B. The quadratic form is that, so as I just also play a trick that I didn't want to handle A, B separately, so I just put them together. So I just let, for example, I just let a new matrix K to stand for our A transpose of B. Okay, so this quadratic form just say that, just back a little bit. Okay, this is our quadratic form. So if X transpose times K times X, so it's will equal to which value? So it's I from 1 to n. So it's our here is n dimension, j from 1 to n, kij times xi times xj. Okay, kij times xi xj. So we just copy this value. Maybe I just go to the next page. So here we have the X transpose Kx, where K is our A transpose of B. And we use a Kij to stand whose ij's element. And ij's value is from 1 to n. X transpose of X, we just copy the things we written down earlier. So this one is a Kij, Xi, Xj. Well, so this is our AX and BX inner product. So we want to do this one again, trying to show, so what is the derivative for this term? So nabla X transpose Kx. So whose is defined as a partial derivative for x1, X transpose Kx, until the xn, X transpose Kx. Okay. Well, how about we can just do this one by one, okay? So how about for the partial, for the x1 part? So when we're taking the partial derivative, we just focus on where the place we have the x1. So where we can have the x1. So it's n times n vector, n times n element together. So where we could have the x1, where we could have the x1. So maybe just write down, I just write down this approach. You can more easily to get what I mean. So here is a k11, x1, xj, x1, and k1n, x1, xn, and kn1, xn, x1, and until the knn, xn, xn. So what I'm trying to do is trying to put this n times n element in a matrix. So, and this value is just all the elements add together. So, and therefore, if we want to find where is the x1 appear, so we know this column, this row have the x1, and this column have x1, and other place do not have any x1. So here I have the x1, here I have x1. So therefore, when we're taking the partial derivative for x1, so we are actually trying to take the partial derivative for this guy, the sum of the first column and sum of the first row. But this one can only be added one time, okay? So it's just like k11 x1 x1, and I just add the remaining value in the first column. So it's I from 2 to n. So which is let me see. So ki1 xi x1. Okay. And adding the remaining row. So in the remaining value in the first row. So it's also I from 2 to n k1i x1 xi. So we just need to take the partial derivative over this size, this size. So let's just see what is the value. So you can definitely do by yourself. Okay. So the first one will give us 2k11 x1. So it's just like the x1 square. So we obtain the 2k11 x1. And for the second part, we can treat it this one as a, so x1 is their common element. So this whole term will look like this guy times x1. So when we take the derivative, so we obtain the I from 2 to n ki1 xi. And the remaining part, we can also do the same. So we can just change this guy a little bit, xi x1. So we also treated this one as a whole term, so which will result into I from 2 to n k1i xi. Okay, a little bit difference, these two terms. So this is ki1, this is a k1i. And then here is I from 2 to n, I from 2 to n. So we can just combine this. We can add a term here, add additional term here, so which will result into the summation I from 1 to n ki1 xi plus the summation I from 1 to n k1i xi. And then, so we just obtain the first value. So you can try for the x2, we just consider the second row, second column and the second row. And for x3, we just consider the third column and the third row. So on and so forth. So the last one is the last column and last row. Therefore, we can find a phenomenon is that this nabla x transpose kx will equal to our first element. I just copy this one directly. And the second element is just to change this 1 to the 2. And so on and so forth. The last one is the change the I from 1 to n, kin xi, adding the I from 1 to n, kni xi. Okay. Well, this is our nabla over the x, so it's given as this format. It's still a little far from our results. So is that here we can also do some organization over this two term. So the naive thinking is that we separate as a two vector. So the first part add the second part. So we add them separately. So the first one we can find. So there is a matrix K. K11 to KYN. KN1 to KNN. And the matrix and the vector x1 to xn. So we can easily find once we want to use the k times x. So this value times this value. So it stands for this term. So this is a k, the first element, the first row times this one. And this, what is this value here? Is the first column times this value. So therefore, and also for the second one, so like this value, so it's the second row times this value. So it's not hard to image that the second term is k times x. And but what is the first term? The first term is use the column times the corresponding x. So we know the product. So if we want to change this column to the row, so you just taking the k transpose x. So therefore, the k transpose of x, you will use the column times the corresponding x. So therefore, whose result will eventually become k transpose x, adding the kx. And also, back to our earlier statement, k is a transpose b. So therefore, whose value will eventually become a transpose b transpose x, adding the a transpose bx. So it's a b transpose ax plus a transpose bx. Okay, so we have just to finish this part. And then we can just back to our earlier statement. So which is pointed out here. Now, maybe I need to some slides to, okay. So now we just wanted to do the nabla for this FB. So we just do the gradient for this one, and this one. So the first term will result into 0 because there is no b included here. And second term is that zb and y. So I just mentioned that we can treat it as a z as a, this y as a c. So whose result will become z transpose times y. So it's a 2z transpose times y. And the last one is that we treat z and z as this a and b. So they are just the same. So it's 2 plus z transpose z and y. And there's no y, it's a b here. Okay, so we have already find the nabla fb function. And maybe I just back to here. Okay, so we can use this same style to write down. And the next step, we will try to solve this equation to making this term is 0. Okay, so how we do that? So the reason that we're trying to do this one is trying to this one will just find the minimum point. Just back here. And we just reorganize this term, so that will become 2z transpose y equal to 2z transpose z times b. Okay, so we can cancel the 2 first. So it will correspond to z transpose z times b equal to z transpose of the y. Well, so if this term is a matrix, so if this term has the inverse, so if have the inverse, then the b will equal to z transpose z inverse z transpose y. And this will be our least square estimation. So we have written down here. Okay, we have written down here. Well, but you need to pay attention that I just mentioned a statement that this one should have the inverse. Okay, so this one should have an inverse. Okay, so this is a least square estimate. We So we just calculate the detail about how we find this least square estimate. So we also have the slides for that, but may not have the details calculation as I'm writing down here. Okay. So just before the taking break, I also want to share another kind of technique that you can do for this S function directly. This function directly. So here, this S function is given as this value, okay? Y minus ZB, the norm of this term. So we can also do for the one dimension case that, for one dimension case, it's just like the Y minus the ZB square. So you definitely know how to take this one. So this one dimension just stands for each of them are just the constant. So we know that this f prime function, so we're equal to negative z times 1 minus zb. Okay, so and the additional 2 here, additional 2 here. So this is the reason. So how we do that? We first treated this term as a whole term. So we just use the chain rule to do that. So first we taking this whole term as a whole body. So we obtain that there is a 2y minus zb. And second step, we taking the y minus zb, taking the derivative for the b part. So we obtain the negative z. So eventually we obtain the 2 negative z y minus zb. Okay. And we are wondering whether we can do the same things for the matrix form. So you just copy 2 minus z y minus zb. Of course, we should need to check whether size is right. So this guy must become r plus 1 version because b is r plus 1. So this guy is n times 1. So this z is n times r plus 1. So you will find the size is not match. But how could you use this one times this one to create the r plus 1 version? So it's just like the transpose y minus zb. Okay, so when you calculate this again, so it's a 2 times z transpose y plus z transpose 2 times z transpose times zb. Okay, so this trick can use this one directly here. So just the same as our solution. Okay, same as the solution. So it's just some small tricks that it may not necessary to just do the whole part, but you can just directly use this trick to find the solution. Okay, so maybe it's have too many kind of the technical detail. So maybe we just take the 10 minutes break. Okay, after break, we will just have a discussion on the inverse about this part. case that this Z transpose Z is invertible. Okay, so here we will just involve a little bit complicated that another kind of concept. So which we call it as a rank. But it's okay if you cannot catch that. But later on we will just emphasize what is the key things you need to keep in mind. Wow. So in matrix, there is thing we call as a rank. So here, this record or Z, so it's a n times 1. Oh, it's not n times 1. So it's a n times r plus 1 matrix. And now we want to discuss whether the Z transpose Z is invertible or not. So this term is r plus 1 times r plus 1. And there is such kind of the thinking is about. So sometimes we need to, we know the invertible just stand for the eigenvalue of this term. The eigenvalue of this term is all non-zero. So that's we can state that this guy is invertible. And commonly, so there is another way that we talk about the invertible. That is called as a rank. So the rank naive thinking is just stand for so how many type of the eigenvalue you could have, or in other sense, it's just stand for if you treated your column vector column. So there is how many linear independent, but it's okay if you just cannot catch that part. But the things we want to emphasize is that the rank of a matrix. So we want to say the rank of a matrix is always smaller or equal to the mean of the column size and the mean of the row size. So this is the rank. And another key concept is that, so the rank of the Z transpose Z is smaller or equal to the rank of the Z. And if you want the Z transpose Z inverse exist, there is another necessary and sufficient condition or equivalent statement is that rank of the Z transpose Z is R plus 1. Okay, so now you could kind of find some phenomena is that if we combine these two equations, this inequality together, it just told us the rank of the Z transpose Z is smaller or equal to the rank of Z, and smaller or equal to mean of n r plus 1. So if we want this one is invertible, so there is a necessary condition that n must larger than r plus 1. N must larger than r plus 1. We can see what if this one does not hold. If n is smaller than r plus 1, we will know rank of the Z transpose Z is smaller or equal to n. So because the minimum is n. And meanwhile, n is smaller than r plus 1. Okay, so this guy is smaller than r plus 1. Then this term does not exist. Okay, so here it just told us a very, very naive case. Shown that our least square estimate may not exist. So we cannot take the inverse is the case that n is smaller than r plus 1. So this is this statement I wanted to show. So n at least it should larger than r plus 1. And also the Z have the rank is r plus 1. Okay, just this type of statement. And with this statement, this guy can guarantee the Z transpose Z inverse exist. Therefore, we can obtain this beta hat. Okay, so this is one kind of necessary condition. But of course, so we should have a key understanding about, so what is this necessary condition stand for? So this is a necessary condition, okay, write down. So what is this n smaller than r plus 1 stand for? So we should guarantee that n at least is larger than or equal to larger than r plus 1. So this is a necessary condition here. So here n stand for, so the number of data. I just use this one to stand for the number of the data. R plus 1. The number of parameter. Unknown things, or just like the feature dimension. So this simple case just told us the data must equal or larger than the feature. So the necessary condition is that. So this is the implied underlying assumption that the number of data must be larger than the dimension of the feature. Okay, so this is a common, so this is a key assumption. So underlying this least square estimation, we need to guarantee once we collect the data n is larger than or larger or equal to the r plus 1. So this is you can find this is always the key assumption or key kind of thinking that in lots of machine learning methods that require the number of data should larger than the number of feature. Well, and so so this is the common argument. So that is we should have the enough large amount of data to guarantee we can have the solution. So just this statement just stand for the number of data larger than number of parameter. And there is also some kind of so just nowadays, the people just rethinking about this kind of assumption. So whether it is true, whether it's necessary that data should be larger than the parameter. Well, but for our example here, for this linear regression model, that this one is just appears very necessary. But just if we go to more complicated model, so just at the earlier stage of the deep learning model, so you probably know that there is a kind of phenomenon we call it as a over parameterization. So that stands for the parameter is larger than the data, just like in the deep neural network. So our parameter just corresponding to the weight and the bias. So commonly we will have, so also just like you heard about the large language model have how many billion of the parameter. So that is just corresponding to the same things. It's just corresponding to how many unknown things, how many unknown parameter. Then you just need to tune to find the parameter to fit in your data, and then that is how billion of the how billion of the model just stand for how billion of parameter. So but commonly, so you could think about whether we have the billion of the data to train the model. Okay, so commonly, so in deep learning model, we don't have the enough data. So n is always smaller than the parameter. But that kind of case, you can still have a good performance. So that is beyond the scope of the things we just talking about here. So necessary condition. So that is scope which is called as a over parameterization. So even though you can have more parameter, but you can still find some good solution if your data is not large enough. Okay. So this is some state of art research topic, just some connection with our conditions presented here. So in the classical machine learning method, this is always a key assumption. But here we need to rethinking about whether it could true. Okay. But for the linear regression, you definitely know you must have this one. But if not, this one do not have the inverse. Do not have inverse. Okay. So this is about our least square estimate. And maybe we just take a simple example, okay? And then we just go to talk about some properties about the beta hat. So here is just some slides that involve the calculation we have already shown. So if you can also take a look. So I guess I probably use a little bit different way. So as I presented here, it's just another angle to compute. Well, we just consider a simple example and to see how it just obtains the least square estimate. Just maybe a little quick. So just involve some type of calculation. Now we just also consider this two-dimension case that beta 0 and beta 1 is our unknown parameter. And our data is given at this table. So where Z1 is we have 5 data in total. So this is the first, second, and the last. So we can write down, so based on the data, we can write down what is the matrix Z here. So because we know our solution will eventually become the Z transpose Z inverse times the Z transpose Y. So as we just, it's just a two component. So this inverse matrix and this part. So we just need to calculate them separately and then we can find the beta hat. So what is the Z given here? So when we're trying to write down the Z, so we always keep in mind, so there is a beta 0, okay? There is a beta 0. So which means that there is a hidden feature. So it's a beta 0 times 1. There is a feature is 1. So we just write down the or 1 vector here. And second type of feature is here. So it's a 0, 1, 2, 3, 4. So it's a, and then RZ is just given as this style. So it's a R is n times R plus 1, where n is 5, R is a 1. So it's a 5 times 2 matrix. And Ry is just copy this 5 value. Okay. And then we can obtain the Z transpose Z. So we just need to, we have the Z and Y. So we can compute Z transpose Z and Z transpose Y. So separately. So this is the Z transpose Z. And then we can also use to find the inverse. So inverse, you can, if it's a calculator or computer, it's a very easy way to do. But if you want to calculate by hand, so I also give you one choice. So for any matrix A, given this style, so whose inverse must satisfy this property? Okay, so this is inverse. And then we can just based on the Z transpose Z, we know what is a 4 element, and then we can find the corresponding Z transpose Z inverse. So it's here. So this just to show a calculation procedures. So Z transpose Z is just from here, and the inverse stamp is just coming from this stamp. So it's just for 2 times 2 matrix. And for multi-version, it will be much more complicated. Okay, but if you have the calculator, you can easily to get the answer. And meanwhile, so we have the Z transpose of Y. So eventually we just combine our Z transpose Z inverse, so with our Z transpose Y. So we can obtain our final least square estimate, so which is 1 and 2. Well, so I think you probably can just no, it's just some calculation. We already know the formula how we just calculate them. Okay, so if you have a question, you can just ask me after the class. Okay, and I also just have one for your exercise, so you can just also do as your exercise after the class. It's just some common calculation, but also a good kind of the opportunity that you can review the content we just mentioned today. Okay, now we have already finished how we find the least square estimate. So now I would like to propose some question for you. Okay, propose some question for you. It's just like our original model is just to say Ry is equal to so beta 0 plus beta 1 Z1. So this is our linear model, okay, with some assumption, of course. And what we are trying to do is that we given the data, we find a least square estimate. So it's here. So maybe a little bit different notation. I use a small y. Okay. So both of them just from the data. So one open question is that it's not open question. One question we need to answer is that what is the relation between the beta hat and the unknown beta that used to generate the data here. So we know here our solution have the several steps. The first step when we want to do this regression problem, we just assume that y is generated from some model, from this linear model. If we will adopt this one, so we need to further to rethink about. So what is the relation? So this linear model have some unknown parameter. So it's some underlying parameters, some underlying things that determine how the z1 to zr generate the corresponding y. And now what we observe is that only part of data. So we just according to this model and obtain some type of the data. Okay, some type of data. And now we use this type of data to calculate the least square estimate. So as you see, when we call this thing as an estimation, estimation must try to estimate. So this beta hat, our idea is trying to use this beta hat to replace the beta 0 to beta r. But a question is that, so whether our beta hat is close to beta 0 to beta r. So that is close to beta 0 to beta r. So just I can ask you, so because I mentioned that this one called as estimate, it's just something from the eigenmean of y minus zb square. Okay, just come from here, come from the data. And well, you know, here I just told you that we just want to minimize this kind of the Euclidean distance. So y and zb Euclidean distance. But have you ever think about whether you can consider some other things? So maybe back to the earlier page. Well, let's just go to the earlier statement. So this is our function, okay? This is our function. A very, very straightforward consideration is that whether you can change this square to the absolute value. Okay, change it to the absolute value. So that is also makes sense because it also stands for the distance. So if we can find a b to make this absolute value as small as possible, you will definitely get another estimate. So therefore, you can try into, so why not try into the power of 4? So it's just like everything it could make sense because you just want to find these two parts as close as possible. So and you choose the absolute value. So if this one is as small as possible, also just indicate these two are close. So therefore, the least square estimate is just the one approach. So it's just the one approach. So we call as an estimate. It's just we want to use this beta hat to know. So this is how the world work. So how the generating mechanism of the data, and we observe part of data, and we want to know what is the underlying pattern of thing. But we have so many choice. Least square is 1. And some other I mentioned, you can use absolute value, use the power of 4. You can also give some other result. So a very important task is that we need to understanding what is the beta hat with this type of things, beta 0 and beta r. So this is something. So we just know how to estimate. Next step we need to know what is the beta hat it is, what is the relation between the beta hat and the beta presented here. So maybe we use a beta star to stand for how the beta is generated. So the data is generated from this beta star, and we just use the data to trying to recover the beta star. So the way we use it is beta hat. Okay. So next step, we're trying to know what is the distance between these two. So, but before that, we can just have some simple understanding. Okay, simple understanding. So this guy is some random variable just because the epsilon is a random variable, have some randomness. The data have some randomness. So therefore, the beta hat is also random. So this is a key concept. We will show it later. Okay, so our next step, our remaining part, will have the two stage. So one kind of key component is that how we understanding the difference between these two. Okay, another type of thing is that we need to further to just best on more things about to understanding about what is the least square trying to do, and then now our next step is trying to know what is a beta hat property. Okay, so we firstly we're trying to use another angle to understand what is the least square estimate trying to do. This one is our first property. So it's here in this step, we do not study the beta hat. We just study the how the least square want to do. And our next step is trying to study what is the beta hat property. Okay, so our first property is called as a orthogonal decomposition. So once again, so because we have so many estimates, so we're trying to, I just propose several for you. Now we just want to know what is this estimate. Is least square estimate play a role here? Now suppose that our Z transpose Z is invertible. Just in guarantee we can calculate our least square estimate. And then after we obtain the least square estimate, so it's the Z transpose Z inverse Z transpose Y. And then, so given a data Z, so we can have our training prediction on our, we can have the prediction on our training data. So maybe we define as a Y hat. So just use a Z times beta hat, okay? So this is how our model looks like. So this is our already some things we have already estimate, and this is our training data, so the feature. So we time them together is our prediction. So this is our prediction value. And we can also define our prediction error. So it's a Y minus Y hat. So this is our observation, our prediction. So it's a residual error or the prediction error. So the first property we know is that this guy is a vector, this guy is a vector, so they are orthogonal to each other. So this is something we stated here. So epsilon hat and y hat is equal to 0. And more importantly, so this y, or just because this angle, this in orthogonal, so we have this type of the equation, so that our data, our target y is actually decomposed as two parts. One is our residual, another is our prediction. Okay, so how we understand this one? So at the first moment, this one is quite weird, but actually this have a more kind of the geometric explanation. So maybe we just see the explanation first and then just demonstrate this type of the property. Okay, so here we can observe one thing is that we just look at, so what is our y hat? So first of all, just in case you forget, I just write down the dimension, okay, dimension. So this dimension is n times 1. It's also n times 1. So we know the y hat is actually a representative of the beta hat. So y hat could be regarded as a z times a beta hat. So now we will involve some things we call it as a feature space. So let me just let you look at, so what is a z first, in case you forget. So at the very earliest stage, we have already shown. So here is a matrix Z. There's a matrix Z. Matrix Z is is n times r plus 1. So here is a r plus 1 column vector. R plus 1 column vector. So when we use the Z hat and the times the beta, so actually we're trying to use this r plus 1 column vector to make some combination, and then it will become our y, okay? So let me just back a little bit. Now, what I want to emphasize that, so actually y hat is represented as a column vector of the z. So it's represented as a column vector of the z. So because y hat is just computed as a z times a beta hat. So z times a beta hat. So z is just the r plus 1 times it's n times r plus 1. Okay, so we can have the r plus 1 column vector, and z times beta hat is just stand for the first column vector is timing with the beta hat 1 plus the second vector times the beta hat 2 until the last vector times the beta hat n. Okay, so we're adding them beta hat r plus 1, and we're adding them together. That will become our y hat. So therefore, we can just treat it z as a, so it's a 1, z1 until the zr to stand for everybody's 1 and everybody's first feature, everybody's r's feature. So we have the n plus 1 together. So now we will consider this feature will span a space. Okay, span a space. So this is a space spanned by this column vector. So it's a range of the z. So we haven't mentioned this one before. So it's a range of the z. So just a column is spanned by the column vector of the z. And our y hat is just one vector in the range of z. So it's just because it's just presented with a coordinate beta hat. 1 hat. And our y, our target. So this is the n plus 1 dimension space. Oh, it's not n plus 1, it's n dimensional, n times 1 dimensional case. And then our y is just also n times 1 dimension. So it's just any arbitrary vector. So this is our y. And actually, what we are trying to do, we just want to find a vector. So in this type of the space, which is closest to our vector y, which is closest to vector y. And this theory just told us that we obtain this closest y hat just because when we just make a decomposition over y and y hat, actually our y hat is just this one. So this is our y hat. And the residual is epsilon hat. So we just write down in a multi-dimension case. It's an n-dimensional case. So this is our y hat. This is epsilon hat. This is the y. So the first one just says these two product have the inner product. These two vector have the inner product 0. Just states this one and this one have the angle is a 90 degree. So it's a 90 degree. So because it's a triangle with a 90 degree, so it's a triangle, okay, triangle with a 90 degree. So we have this famous result that the length of the square of length of y is equal to the square length of epsilon hat, adding the square length of the y hat. So it's very famous for the triangle with a 90 degree. So therefore, it's just told us, so this theory just told us what is the least square want to do. So commonly, we would like to call this range of z as a feature space because it's just presented by the feature. So maybe I write down as a feature space. And our y is any vector, okay, any n plus 1, n times 1 dimension vector. So this just told us one thing, our estimate is always trying to find a projection from y, our vector, to our feature space. So the orthogonal just stand for its projection. So we probably have known this one from the high school part. So that the projection just stand for the residual have this one is just with orthogonal to each other. So projection is orthogonal to the residual, just a stand for it's a valid projection. So which also indicate this one is the smallest distance compared with this term. Okay, so naively speaking, so this theory just told us this square is a projection from our target variable to our feature space. And so this is just so this is why sometimes this square will make sense just because we're trying to build the connection. We want to build the connection with our target and our feature. So here we just the connection we build is trying to make the projection to our feature space. Okay, so but of course, so this is just for this square. And for other estimates, so it may not have this kind of the explanation. So this is why this one is more commonly used. Okay. Now our remaining task is trying to demonstrate this epsilon hat and y hat is equal to 0. So this is a series. The series just told us there is have the feature. The feature is well, so the feature itself is generate a space. So just this plane. So it's a plane here, and this is in the Rn dimension version. Okay, and the feature is just the r plus 1 vector combined together to split a hyperplane or just a plane. We just call here. So, and for any y, we just make a projection trying to this feature space. So, and our prediction is just here. Well, so our next example is trying to show what is a relation. So how this one is true. Now, we just want to demonstrate the epsilon hat and the y hat. So it's orthogonal. The inner product is 0. And the remaining part is very easy to do. It's just because this is a famous result for the orthogonal part. Okay, so our y hat is given as a z transpose z inverse. It's not y hat, it's a beta hat. Z transpose y. And our y hat is given as a z times beta hat. So it's z times z transpose z inverse z transpose y. And our epsilon hat is given as a y minus y hat. So it's a y minus z transpose z inverse z transpose y. So we can regard the first y as a identity matrix times y. So therefore, they share the same component. That will result into I minus z transpose z inverse z transpose y. Okay, so our remaining step is trying to show the inner product between these two are 0. So naively speaking, we are trying to show that the epsilon hat transpose times y hat is 0. So we have no choice just to write down the whole kind of the content. Okay. For the first part, when we're taking the transpose, so actually you could check. So this guy will equal to y transpose and times the transpose of this part. And actually, so this guy and this guy is just equal to, oh, it's not a minus, it's I, when we take the I transpose, so it's still the I. And the remaining part, we're just taking the transpose for each one by one. So it will become the Z transpose, take additional transpose, and the Z transpose Z inverse, take a transpose, and Z transpose. And we're keeping the other part. Okay. So one thing we can observe is that this guy, so it's a Z. So this guy is a Z transpose. What is about the intermediate part? So Z transpose Z inverse takes the transpose. The good thing is that this term is symmetric. That states the transpose is equal to itself. You can easily to check just because Z transpose Z is symmetric and whose inverse is also supposed to be symmetric. So therefore, the whole term will become like this stem. So we just keep in this part as a content, a whole component, and this part as a component, this part as a component. We just handle the intermediate part. This is the first step. Second step is just the same things timed together. So this type of thing is only looks complicated, but you can find once you make this thing timed together, they are just the same part. So which means that this two term will cancel as an identity matrix. And the whole component is same as this one. So the intermediate part is 0 times y. So it's still 0. Okay, so that is finished the inner product between epsilon hat and y hat. Actually, it's just looks like complicated, but just because these properties. So here it's just record some things we mentioned at earlier, that we find the z times z transpose z inverse z transpose. So this kind of matrix time itself is still this guy. Okay, just we just make use of property that a square just means times is twice is still this term. So this just indicate this one is a projection matrix. Projection matrix. Okay, so this is also just a y. It's not project, it's projection matrix. Okay, so it's just the states that y, it's just we mentioned here as a projection part. So it's just making such kind of projection. So you can say that the beta hat is just a y times this component. Okay, so if you just look at the y hat again, so it's a z times this component times a y. So y hat is z times z transpose z inverse z transpose of y. So this term we have already shown is a projection matrix. So you can see this is why we call it as a projection. Y hat is a projection from y to this part. Okay, this is a projection matrix. Well, so this answer our solution. So the projection just stands for that the projection terms we mentioned as this size. Okay, so this is a common geometric understanding among what is a least square. It's just to do this type of the orthogonal projection. Okay, so this is the first properties. So actually, so it's very easier to understand. So when we want to make the prediction of our y, we want to get the prediction of y hat. So you must focus on the z you have. So it must come from the z. So therefore, it's very natural that when you make the prediction we're making here, you must rely on the z. So therefore, your problem is that how, according to your z, to find a good prediction, how to find a prediction. So which means that here is your y. So there is your observation, and your prediction must relate it to this z space. So therefore, it's very natural that our prediction is just taken as a projection of y on this z space. Okay, so we call it as a feature space. Okay, so this is our first property. Well, you may also take a look. So we have some kind, so this have the details calculation, but it's almost same as the thing I mentioned. So you can just take a look. So it's a little bit different. Well, the second thing is more important. So it's called as a distribution of the beta hat. So we want to further to understand what is a beta hat it is. Okay, so we have mentioned that our generative mechanism just to show that there is a beta star that depends on how our data is generated. And the beta hat is just one thing we obtain from the our data. So it's just like the beta star is how the word will work. And our observation is just one part to look at the word. So just according to our data. And then we just want to know what is about our estimation with the ground truth. So this is our second step, trying to show what is the distribution of the beta hat. Well, so one thing we need to take additional time is just because that the beta hat, I mentioned that. So we have assumed that y is equal to z beta at the epsilon. So epsilon we mentioned is have some randomness. So therefore, the y is contain such kind of randomness. So therefore, it just stand for our data y part have some randomness. So therefore, it's not easier, not hard to image. This guy is also random, the least square, because it has the y. Y is random. So therefore, the beta hat is random. So how we understand this random? So maybe just like there are several parallel world, and at a different world, you just taking the different sampling about the observation, and you will get the different least square estimate. But in our reality, that we only have the one realization. So this is how you just calculate the beta hat you obtain is just one realization of your random variable. Okay, so now we wanted to further to understand. So what is the variable it is? So even given the one realization. So our next theory will just say, so if we assume our epsilon, so it's a Gaussian distribution, a Gaussian random variable. I mentioned this one is not such kind of necessary, we'll explain later. The beta hat is a Gaussian random variable. Okay, beta hat is a random variable, and whose distribution is a normal or called as a Gaussian distribution. And the normal distribution has the mean, which is a beta star, and have the variance is presented here. That is to see one hour observation, 1 hour realization is just around the ground truth. So we just around the ground truth. And how different it is, it's just because they have the variance. So this is also the reason. Maybe I just back to the last page. So when you just use any kind of package to calculate the linear regression, like this Python package stance mode, so it will tell you the coefficient part. So the red block just told us what is our least square, and also have this yellow block, so which told us what is the corresponding Gaussian standard error in the Gaussian variable. So because we know this is just a random one realization of our random variable, and we also know what is the standard deviation, and also the p-value is trying to quantify. So what is the distance between our what is our ground truth with a zero. So this type of things. So So it's just told us sometimes we only care about the prediction, or it's okay that we stop at with this kind of estimate. You just care about prediction, but in some kind of scenario, the people will also concern about whether the ground truth is close to zero or not. So especially in lots of the biology, in lots of the kind of the clinical trial or some kind of econometric model, the people will always consider about this guy. You probably heard the name. This name just called as a p-value. So p-value just come from this Gaussian, no, Gaussian random variable. So this is the next step we will try to finish. But well, because this is contains so many things about randomness, so I just suggest that you can first take a look about the remaining part. We have some quick review about the probability concept. So I will suggest you to have a review so about that part. So we may not go to the detail. So, but it's just a little kind of a lot of content. So included in the following page. So we will follow this one quickly next week, but I will highly suggest that if you have not familiar with this part, just to take a look after the class. Okay, so maybe we just stop here and we will just we stop here and see you next week.